Alright, so in chapter 28, we learned about how capacitors, resistors, and batteries play a role in directional circuits, as the direction of the current goes in one direction. But in some circuits, the direction of the charge will switch at its half-life, which results in a sinusoidal graph, with the peaks representing the peak EMF produced by a circuit. In chapter 32, we are looking at how circuits that have an oscillating electromagnetic force, also known as alternating current circuits or AC circuits. So an AC circuit induces an instantaneous EMF, measures the rate of change of a magnetic flux through the circuit. It is written out as epsilon equals epsilon naught cosine omega t. As a function of time, the omega represents the angular frequency, and epsilon naught as the peak EMF the circuit goes through.
To represent sinusoidal varying voltage and currents, we will be using rotating vectors, which are phasors. Phasors are counterclockwise rotating vectors about the origin, which represent the projection on a horizontal axis with a length equal to the magnitude of the quantity. The phasor angle is given by angular frequency known as omega, which is also given as a function of time. The length or magnitude of the phasor is the maximum length of the quantity, which represents the peak EMF. A phasor diagram are diagrams just containing phasors. As you can see on the image to the right, the phasor diagram for the inductor circuit shows that the current lags behind the voltage by pi/2. And on the image to the left, the plot of the instantaneous current and instantaneous voltage shows that the current lags behind the voltage by pi/2. They represent the exact same thing, but one is a plot and one is a phasor diagram. They are labeled for a clear understanding.
The capacitor circuit consists of a capacitor and a resistor connected either in series or parallel to a voltage or current source, or also known as a RC filter. Take the simple RC circuit. While the switch is open, the maximum value in this case is 12 volts across the resistor and read 0 for the capacitor. But when the switch is closed, the resistor voltage will discharge to 0 and charges the capacitor to the maximum. The time it takes to charge the capacitor can be found by solving for the time constant, which equals to resistor times capacitor times 5 and has seconds as units.
Similarly, we can find the potential difference in the current as functions of time by the following. Given the time, peak voltage/current, and the strength of both the capacitor and resistor, the following two equations are given for both voltage and current. They basically explain if the inductor in the circuit, the current decreases more slowly, specifically exponentially. The time constant regulates how fast the system reacts. A small time constant equals a quick evolution, and a large time constant equals a slow evolution. As you can see in the image below, the graph clearly shows an exponential decay, which is what is being represented by the two equations above.
Like RC units, resistor, inductor, and capacitors are connected to produce what are known as RLC circuits. Similar to RC circuits, when the first switch is closed, the capacitor is charged due to the battery source. After completing the connection to the inductor, the charge stored in the capacitor will move towards the inductor and charge it. Once the capacitor is fully discharged, the inductor will start discharging back into the capacitor. This way, charges will flow to and from the inductor and capacitor. But since there will be some charges lost in the process,